Hello everyone, welcome to my video on use substitution or the substitution rule. So this is our first integration technique that we're learning, and in my opinion it's the most important one. Why? Because perfecting use substitution is going to give you the ability to simplify difficult integrals, whereas if you use the inappropriate use substitution or the wrong substitution, you can make your life a lot more difficult. So perfecting this is really important, and the issue with this is that there's many different scenarios, so the strategy that I'll provide may or may not always work. So let's look at the claim. So use substitution states that if you let u equal g of x, so you're calling this function g of x u, which is differentiable, we could take its derivative, on and whose range is capital I, so the interval I, and f is continuous on that interval, then we say that the integral of f composed of g of x times g prime of x, the derivative of what's inside the f, dx, is equal to the integral of f of u du. So what is this telling us? Well, essentially, if you're given a function or a composition of function, use substitution is the Cal 2 equivalent of chain rule. So we're essentially doing chain rule for integration. Okay, so in Cal 1, chain rule was difficult, but in Cal 2, when you perfect use substitution, it makes our life a lot more easier. So but essentially this is the integral of composition of functions. And what you have to notice is that the function on the left-hand side, or the left-hand side of the equation, is written in terms of x. So it's in terms of the variable x, or whatever you started with. And what we're going to do is we're going to transform this by making a substitution, a clever substitution, into something that's written solely in terms of u. There's no x's over here. So this is expressed solely in terms of u. And now we transformed it into something which is easy to integrate. Okay, so at the moment, all we know are the basic integrals from our previous video, our 14 basic integrals. But now we're able to integrate functions that resemble what we started with, but have slight changes. So let's go ahead and look at a couple of examples. The other thing is I'm not going to prove this, so if you wish to see the proof, let me know, and I'll do that in a separate video. Okay, so let me know in the comments if you would like to see an explanation of the proof for use substitution. Okay, so the biggest issue with use substitution is, what do we call our u? How do we know what to let u equal to? We have to let u equal a function, but what is that function? Well, here's a strategy that I'm going to provide you with that, again, will not always work. It depends on the situation. So every situation is different. The more you practice, the more you're going to have a better intuition of what you should let your u equal to. And you're going to make mistakes in the beginning. It's normal. It's part of the process, but it's learning the mistakes, which is important here. So let's begin with calling u the function which is inside the root. What do I mean by that? Well, let's say you have an integral of the square root of x plus 1 dx. Well, in order to solve this, you're going to let your u equal whatever's inside the root. So we'll let u equal x plus 1. And this substitution is going to solve this problem. I'm not going to solve it now, but I'm just showing you how to choose your u. Second one, I wrote inside brackets. In brackets, well, if you have the integral of x minus 1 to the 100th, and you have to integrate this function, well, one way of doing it is expanding, but you don't want to expand 100 times. So you could solve this problem with a u substitution. Letting u equal what's in the bracket would work. In this case, letting u equal x minus 1 would allow us to solve, to integrate this problem over here. Next one I wrote in the denominator, if you have the integral of, let's say, sine over cos, so sine x divided by cos x, well, letting u equal cos allows us to solve this problem. So u equals whatever's in the denominator. Cos is on the bottom, let u equal cos of x, and go ahead and solve. In the exponent, what do I mean by in the exponent? Well, if you have e to, let's say, the 2x dx, the exponent of the e is 2x. So we're going to let u equal 2x, and that allows us to solve this problem. So this is what I mean by in the root, in the bracket, in the denominator, in the exponent. So these should be one of your first initial candidates to attempt, okay, depending on the situation that you're dealing with. The second trick, well, the second step, which is an important trick, and this is the one that I use the most, I look at my u and I think about its derivative. Whatever I'm about to call u, or whatever my candidate u is, I think of its derivative and I look to see if the derivative is sitting in front. Okay, this is a super important trick, and you're gonna see as we practice it more often, you're gonna get a better feel to using step 2. So when you're taking the derivative, when you're letting u equal some function, take its derivative and see if its derivative is there. So if we look at the first one, I take the derivative of x plus 1, the derivative is 1. Is there a 1 here? Well, technically, yeah. There's a 1 in front, but we don't have to write it. And even if it's a constant, if you're off by a constant, that's okay. But essentially what you're doing is you're taking the derivative of what's here and see if it lies in the integrand. Take the derivative of cos of x. What's the derivative? Well, the derivative of sine is cos. The derivative of cos is negative sine. Oh, we have a sine in the numerator. That's a good sign. Okay, so now it means this is the correct u. Okay, so we'll keep practicing and we'll have an idea of why this trick works. Okay, so keep this in mind. So there's just a couple of warnings I want to provide you with. The first one, be very careful. Whenever you're applying a u substitution, you will never use the u substitution u equals x. Okay, that's wrong. Applying the substitution u equals x, all you're doing is you're switching the parameter that you're integrating with respect to. So you're not simplifying the problem, you're just changing the letter you're working with. So that does not help. So this will never be a thing. You'll never apply a u substitution. So you might have to do it for integration by parts, u equals x, that's fine, which is a different integrating technique we'll see later on. But for u substitution specifically, you will never use a u substitution where u is equal to x, okay? So that's my first warning. Save yourself time, don't make this mistake. Another warning I want to provide you with is the fact that your substitution is wrong or incomplete. You have to simplify. If you chose your u substitution, you plugged everything in, and you began with a function that's written in terms of x, or you're integrating a function that's expressed solely in terms of x, and then when you finished integrating it, or you finished using your substitution before you integrate, you have like u plus 1, let's say, and then times x du. So here it's written in terms of x, and then you transformed it and you got this, let's say. The fact that you still have an x here is wrong. You have to ensure that the function you're transforming it to, when you apply your u substitution, has to be expressed solely in terms of u's. Constants and u's, that's it. There cannot be the parameter x anymore, okay? So if there's no x here, then it's fine, it's good, because now it's expressed solely in terms of u's. If you're left with an x, odds are you either made the wrong substitution or you have to continue simplifying, okay? So just be careful for those two things, okay? So let's go ahead and apply our strategy and look at a couple of examples. So let's take a look at our first example over here. It says to evaluate the integral of x times e to the x squared plus 1 dx. How do we solve this? This looks very intimidating. This integral here, actually, if it was e to the negative x squared, we do not have the resources to solve this. Perhaps with approximation techniques or Taylor polynomials, but at the moment we can't solve something like this. Yet if we throw an x in the front, now we're able to solve it using the appropriate u substitution. Okay, so in this case we don't have negative x squared, we have positive x squared plus 1. How do we solve this? Okay, so we have to let u equal something. What are we going to let u equal to? Well, do we have a square root? There's no square root. That was one of the first things we have to look at. Do we have a denominator? There's no denominator. Do we have brackets? There's no brackets. But we have an exponent. So let's maybe try calling it what's in the exponent. So in the exponent of the e, we have x squared plus 1. And our second trick was, let's think of the derivative. So I'm going to go on the side and write, let u equal x squared plus 1. Okay. Now we're going to derive that. What's the derivative of x squared plus 1? So we're deriving u with respect to x. And that's equal to, well, the derivative of x squared plus 1 with respect to x is just 2x, right? And this is a really good sign because the derivative of x squared plus 1 is just 2x. And we have an x that's sitting in the front. This is what I meant in our second strategy, the trick. Think of its derivative. Once you're letting u equal something, think of its derivative and see if the derivative is sitting inside the integral. The fact that it's off by a constant doesn't matter. The constant is not something we're worried about. We really care about just the, let's say in this case, the polynomial. It's degree x, x to the 1. Here we have x to the 1. So this is a good sign. This is something that you should be comfortable with. But now we have to express this in terms of solely u. We want to rewrite this with no x's involved. Okay, so how do we do this? Well, right now this x, there's nothing I could do with it. I have to leave it. In the exponent, we have x squared plus 1, but we used the u substitution. So instead of x squared plus 1, we're going to call that u. So we have e to the u and then dx. Okay, so I just rewrote x squared plus 1 as u. This is an issue because we said in order to apply an integration by parts, to apply a u substitution, it has to be expressed solely in terms of u. There can't be any x's. So we have to remove this x over here and we have to remove this dx over here. How do we get rid of this dx over here? Well, notice we have a dx in our substitution. When we took the derivative, we got du over dx equals 2x. Solve for this dx. Teachers don't usually do it this way. I take the time to actually solve for the dx. So in a sense, we could think of this as 2x over 1, and we could cross multiply solving for dx. So by cross multiplying, we get du over 2x equals dx. So instead of writing dx, we're going to substitute it with du over dx. Du over 2x. So what we have here is the integral of x times e to the u. I can't do anything. With the dx, we're going to substitute it with what it's equal to. So we'll write, instead of dx, du over 2x. And notice the key point here, the fact that when we took its derivative, we knew it was similar to what we have in our integral, or a polynomial of the same degree. These x's cancel. One's in the numerator, one's on the denominator, leaving us with just a 2. But it's not really a 2, it's a half, right? Because you're dividing by 2, and that's just a constant. So since we have a constant multiple, we could take it out of the integral. That's one of our integration properties. Removing the 1/2 on the outside leaves us with the integral of e to the u du. And we went from something which we had no clue about and replaced it with this, which now we know. We know the integral of e to the u, or think of it as e to the x. The letter you're using doesn't matter. And notice that this whole integral, there's no x's involved. So you have the appropriate u substitution. So now that we expressed it solely in terms of u, we could integrate this guy. So the integral of e to the u, one of our favorites, is just simply e to the u, right? But since it's an indefinite integral, there's no bounds, remember, you have to add your plus c. Okay. And stopping here is incorrect. Why? We start in terms of x. So that means you have to finish in terms of x. So I can't write my answer in this form. What do? Well, what's u equal to? U is equal to x squared plus 1. You bring that guy back. Okay, so this is wrong. We're going to rewrite this as, well, not that it's wrong, it's incomplete. You're not finished. We're going to rewrite it as e to the u is equal to x squared plus 1 based off our substitution, divided by 2 plus c. And this is the final answer. Okay. So let's take a look at another example. So in the next example, we have to evaluate the integral of sine x times cos x dx. Why is this an issue? Why can't we just integrate this individually? We know the integral of sine and we know the integral of cos. Can't we just integrate using our basic formulas? Well, in this case, no, because there's a multiplication, so it's not the same. If it was separated by a plus, then yes, you could deal with each term individually. Since it's separated by a multiplication, you cannot separate them. You have to leave them. So we have to solve this using a u substitution, okay? Our basic integration properties do not apply in this case. So how do we solve this? So you should be questioning yourself, what do you let u equal to? Which function do we let u equal to? And here there's actually multiple answers. So if you're saying, I'm going to let u equal sine, I don't know why, just I'm going to try it, that's good. That works. And if you're thinking of using u as cos, that also works. Why does it work? Because what's the derivative of sine? The derivative of sine is cos, and we have a cos that's sitting here. So that's great. Whereas if you let u equal cos, what's the derivative of cos? Well, it's a negative sine. And it's sitting there. It's off by a negative, but we don't care because it's a constant. So the constant we could just sit on the outside. So the fact that the derivative of both these terms are there, it doesn't matter which one you call your u in this case. So for simplicity, I'm going to take sine because I want to work with positive values. So I'll let u equal sine of x. The derivative of sine, so now we're deriving with respect to x. The derivative of sine is cos. And now I'm going to cross multiply and solve for the dx, because you're always isolating the dx here. So you get du over cos x equals dx. Okay. And now you substitute everything into here. So this thing here is equal to the integral. Instead of sine, what are we using? Well, we're writing a u because we're transforming everything in terms of u. The cos of x we have to leave, there's nothing we can do with that. And now we're going to replace the dx, and the dx we know is equal to du divided by cos. And look at that. The x that was an issue here, the cos of x, cancels out as we wanted to. And what are we left with? We're left with the integral of u du, which is extremely simple to solve. If you think of this as, like, you should be thinking of this as the integral of x dx, which is simply just power rule for integration. So how do we solve this? We add 1 to the exponent and divide by that value. So the integral of u squared is equal to u squared over 2, indefinite, so plus c. And this is the answer. So if you got this, good job, but you're wrong. It's not complete. Remember, you start in terms of x, finish in terms of x. Here you express your answer in terms of u. Switch that back. What's u equal to? U is equal to sine. Bring back the sine. So what we really have to complete the question is sine squared of x. All that divided by 2 plus c. And this is the correct final answer. Okay? So let's go ahead and keep practicing. Hopefully by now you're getting a good feel of what's going on and how to apply u substitutions. If you use cos as your u, you're gonna get your answer is probably correct. It may not resemble the one that's over here. Okay, it just may be an alternate form. Okay, let's go ahead and look at another example. So in the next example over here, it says to evaluate the integral, and we have the integral of x to the 4 times cos of x to the 5 minus 5 dx. So pause the video, try to give this a shot, see if you're able to solve it on your own, and try to figure out what the u is going to be. What are you thinking of letting u equal to? Well, using our strategy, we know that we could take what's in the bracket. Will that work? Well, inside the bracket, or inside the argument of the cos, we have x to the 5 minus 5. Is that a viable option? Okay. Or you might have been thinking, let me let u equal x to the 4. Okay. Well, how do we know which one to use? Or why can't I put cos as well? Well, go back to strategy 2. Think about its derivative. What's the derivative of x to the 4 with respect to x? Well, the derivative of x to the 4 is 4x cubed. Is there a 4x cubed or an x cubed in here somewhere? No. So x to the 4 is not something I would lean towards. What about this one here? If I have x to the 5 minus 5 and I take its derivative, what's the derivative of 5x to the 5? Well, that's 5x to the 4. Sorry, what's the derivative of x to the 5? It's 5x to the 4. And we have an x to the 4 sitting on the outside of my cos. So I'm feeling confident about letting this equal my u. So let's go ahead and solve. So if I take my derivative with respect to x, I get 5x to the 4, and the derivative of negative 5 is just 0, so we're left with 5x to the 4. And cross multiplying to solve for dx, you get du divided by 5x to the 4 equals dx. So essentially what you're doing here is you're multiplying by dx on both sides, and at the same time you're dividing by 5x to the 4 on both sides. So we're isolating for the dx, and now we substitute everything that we know. So the x to the 4, there's nothing to do, we have to leave that. The cos has to stay, but what's inside the bracket, x to the 5 minus 5, is simply just u. So we have cos of u. And dx, we can replace dx with du over 5x to the 4. Okay, so over here, the integral we're dealing with is written with respect to x. Here now we're writing the integral with respect to u. So that's why we need du here, and we can't have any x's. But this works out well because this x to the 4 cancels out with this x to the 4, leaving us with a fifth, which is just a constant. So let's pull out the 1/5. So keep in mind the 5's on the denominator here, so it's not 5, it's 1 over 5. And it's the integral of just cos of u du. There's no x's here, and we know the integral of cos. We know the derivative of sine is cos, so the integral of cos comes back up as sine. So the 1/5 is a constant multiple, we leave it in the front, and the integral of cos is sine. Plus c. Okay. Again, don't forget, you start in terms of x, you finish in terms of x. So don't leave your answer in this form. Substitute the u what it's equal to. Okay, so our answer here is sine u is equal to x to the 5 minus 5, and you're dividing by 5 plus the constant. this is the final answer. Okay. So let's keep going, let's keep practicing. So in the following example, it tells us to evaluate the integral of x divided by square root of x squared plus 4 dx. So pause the video, give this a shot, see if you're able to solve it. So we have to figure out what our u is. So I don't know if you were able to do that, but the two main ones that come to mind for me is x squared plus 4 and x. So do we let u equal x? Well, no, that's one of the warnings that I provided at the beginning, that you never let u equal x, so we're not going to use x. What about the x squared plus 4? Well, what's the derivative of x squared plus 4? This is what you should be asking yourself. And the derivative of x squared is 2x. And we have an x sitting on top, so this is a good sign. The fact that it's a derivative, the derivative of my u is sitting in the integral. So I'm feeling confident about that. So let's go ahead and do that. Taking the derivative, we get 2x. Sorry, taking the derivative with respect to x, we get 2x. And I'm going to go ahead and solve for my dx. So I get du over 2x equals dx. Okay. And following our strategies, notice that the x squared plus 4 is both inside the root and down the denominator. So our strategy still applies. This is equal to the integral of x on top, we have to leave it, and the square root of x squared plus 4. And x squared plus 4 is simply just u, so we have the square root of u. And what's dx equal to? Well, dx is equal to du over 2x. The x's cancel, leaving us with a 1/2, so this 2 over here comes out. And we're left with the integral of 1 over square root of u du. Okay. Can we solve this? Well, it looks complicated, but at the end of the day, it's something we actually know. We just have to change its form. So rewriting square roots, we know that's equal to a 1/2, exponent a 1/2. And 1 over u to the 1/2 is the same as flipping this up and switching the sign. So we could rewrite this as u to the negative 1/2. And that's equivalent. And why do we want it in this form? Well, now we have it in the form for power rule for integration. So we add 1 to the exponent and divide by that value. So let's go ahead and do that. We have the 1/2. We add 1 to the exponent, so negative 1/2 plus 1 is positive 1/2, and you divide by 1/2. Okay. So that's the integral, and we add c. Dividing by 1/2 is the same as multiplying by 2, so this 1/2 and this 1/2 cancels. Okay. Because you can multiply by the reciprocal, the 2 comes up on top, and then you have 1/2 times 2, which is 1, so they cancel each other, leaving us with u to the 1/2. But what's u equal to? U is equal to x squared plus 4. So really what we have is the square root of x squared plus 4. Okay. Because you remember, do not leave your answer in terms of u. You have to express it in terms of x, because we started with an integral written in terms of x. Okay, so we have to come back in terms of x. And since it's indefinite, there's no bounds, we have to add a plus c. And this is the final answer. We're done. So in the next example, we're evaluating the integral of ln of x, all that cubed, divided by x dx. So pause the video, give this a shot, see if you're able to solve for it. So choosing your u becomes a challenge here. What should we let our u equal to? Well, again, the x on the denominator, we don't let u equal x, so we're not using that. And we have ln or ln cubed. Which one should we do? And this is where it's difficult. Well, I would take the ln of x. Okay, why? What's my reasoning? Well, I'm asking myself, what's the derivative of ln of x? It's 1 over x. And that's what we have over here. We have a 1 over x. So I'm feeling confident about this. But let's go ahead and solve and see if it does work out. Because if we cannot express this solely in terms of u, then ln of x was the wrong u. We have to call it something else. So let's go ahead and take the derivative. So the derivative of u with respect to x is equal to 1 over x. Cross multiplying here, we get du times x is equal to dx. So I multiply both sides by dx, and I multiply both sides by x, giving me x du, this times this, is equal to this times this, dx times 1. So now let's substitute everything that we know into here. Ln of x is being replaced with u, so let's substitute that. So we get u cubed. and we have x on the bottom. There's nothing we could do about that. We have to leave it. So we're a bit worried about this x, but let's go ahead and substitute our dx. Replacing dx, we get x times du. And this is nice because the x's cancel. So we're happy about that. Leaving us with simply just the integral of u cubed du. So we went from something that's very complicated to something that's super simple. And this is just power rule. So we add 1 to the exponent and divide by that value. So this gives us u to the 4 over 4. It's indefinite, so plus c. Don't forget your plus c. And lastly, we come back in terms of x. So we're going to substitute u with what it's equal to. U is equal to ln of x. So we have ln of x to the 4, exponent of 4, divided by 4 plus c. And we're done. That's the answer. So let's go ahead and keep practicing. So in example 6 over here, it says to evaluate the integral of x cubed times the square root of x squared plus 1 dx. So this one's very tricky. Give it a shot, pause the video, and see if you're able to solve it on your own. So what's difficult about this is identifying what the u is. So were you able to figure out what your u is equal to? Well, the two candidate options I think are x cubed versus x squared plus 1. What's inside the root or what's on the outside? Well, what's the derivative of x cubed? Well, it's 3x squared. Is there an x squared in here? Yeah, but it's inside the root, so that's an issue. So x cubed actually in this case doesn't work. If we take x squared plus 1, what's the derivative? Well, the derivative of x squared plus 1 is 2x. But there's no 2x on the outside. There's an x cubed, but there's not 2x. How do we rectify this? Well, it ends up working out with u equal to x squared plus 1. Okay. The fact that there's no x on the outside, in this case, actually doesn't matter. It's still going to work. Let's go ahead and see why. If we take the derivative with respect to x, you get 2x. Solving for dx by cross multiplying, you get du over 2x equals dx. Let's substitute what we know. X cubed, there's nothing we could do. We have to leave it. And inside the root, x squared plus 1, we're substituting it with u. And dx, we know it's equal to du over 2x. So let's go ahead and do that. So notice the 2 on the bottom, the 1/2 could be pulled out. So let's write that here. 1/2 integral. And only one of the x's cancel. This x cancels with one of them in the exponent, leaving us with an x squared. So we're left with x squared times root u du. Why is this not an issue? We have an integral which we want to express solely in terms of u, but with an x squared in it. Why is this okay? And the answer is, look at your u substitution. So the fact that this is expressed using x squared is okay because we have a relationship between x squared and u. So we could express this integral here solely in terms of u by using the following observation. The fact that, let me do this in red, the fact that x squared is actually equal to u minus 1. You could take the initial substitution that we used in the beginning and move the 1 over. Subtract 1 on both sides, giving us u minus 1 equals x squared. So instead of writing x squared, we could express it as u minus 1. And this is the key to the problem. So this is what I call a tricky u sub. So you have to be very careful for this. Sometimes our strategy doesn't work, so you might fall into a situation like this where you have to look back at the original substitution and manipulate it, okay? So be careful for that. And this gives us a 1/2 integral x squared. We're going to replace it with u minus 1. And square root of u, we're going to write it as u to the 1/2 du. Now the integral is expressed solely in terms of u, so we're able to go ahead and solve it. How do we solve this? Well, you distribute the u to the 1/2. 1 times u to the 1/2 is u to the 3/2, minus negative 1 times u to the 1/2 is minus u to the 1/2. Now we could use power rule on each term individually. So we still have the 1/2 on the outside. Here we add 1 to the exponent and divide by that value. So adding 1 to 3/2 is 5/2. And then you divide by 5/2. Minus, same thing here, u to the 3/2. So a 1/2 plus 1 is 3/2. And then you divide by 3/2. And since we integrated the integral sign and the du, now we stop writing it and we write our plus c. Okay. So a couple of things we have to do. We have to simplify. So we have to, we're dividing by a fraction here. So since you're dividing by 5/2, that's the same as multiplying by 2/5. We multiply by the reciprocal. Okay, so we're essentially dividing fractions. So we have the 1/2 in the front. This we could rewrite it as 2u to the 5/2 over 5 minus, and again here, we could flip the 3/2 to 2/3, u to the 3/2 plus c, okay? Because we're essentially dividing fractions. Whenever you have a fraction divided by a fraction, the u to the 5/2, you could think of it as u to the 5/2 over 1. So you have a fraction divided by a fraction, which is the same as taking the first fraction, leaving it as is, and multiplying by the reciprocal of the second fraction on the denominator. So the 5 over 2 becomes 2 over 5. That's how we get this. Okay, next we could distribute the 1/2. And at the same time, we have to express our answer solely in terms of x. So we cannot write u. What's u equal to? X squared plus 1. Let's replace the u's with x squared plus 1, and at the same time distribute the 1/2. Leaving us with 1/2 times 2/5, the 2's cancel, leaving us with a 1/5, and the u we're going to replace with x squared plus 1. So same exponent, 5/2, and we're left with divided by 5. Minus, same thing here, we're multiplying the 1/2 times negative 2/3, the 2's cancel, leaving us with negative 1/3. So we're dividing by 3, and the u we're replacing with x squared plus 1. But now it's to the 3/2 plus c. And this is the final answer. Okay, so very tricky, be careful, keep practicing, and let's take a look at another example. So in the following example, it says to show that the integral of tan x dx is equal to ln of secant x plus c. So this is one of the formulas that was provided in an earlier video that you had to memorize, our basic formulas. We know the integral of tan x is equal to this. You could have it just memorized, or let's say you forget, we could resort to use substitution to show this. So let's go ahead and use the appropriate use substitution to show this is equal to this. So pause the video, give this a shot, see if you're able to solve it on your own. So to start off, we have the integral of tan x dx, and it's not apparent what to call u. In order to begin, the trick is to rewrite tan. What's tan equal to? Well, tan is equal to sine over cos. Sine x divided by cos x. Okay, and why is this a good thing? Well, we can now integrate this using the appropriate use substitution. Letting u equal what's in the denominator works. This is one that we saw in the intro of this video. Letting u, we said, equal cos, what's in the denominator, is going to work because the derivative of cos is equal to sine, and sine's there. Why wouldn't sine work? Well, if you take the derivative using sine, you might have attempted that. When you take the derivative, you'll get cos, but the cos is going to drop on the bottom, giving you a cos squared on the bottom, which doesn't cancel it, so you're stuck. Didn't work. Whereas if you let u equal cos, when you take the derivative, you're going to get a sine, a du over sine, which is going to cancel with the sine in the numerator, and that works. Okay, so in this case here, u equals sine of x does not work, and making these mistakes again is normal, especially in the beginning, so don't feel bad if you're making these mistakes. So here, let u equal cos of x, take the derivative, the u equals negative sine of x over dx. Cross multiplying to get dx, think of this as over 1. We cross multiply, isolate for dx, you get du divided by negative sine of x. Right, so our sine of x is on the bottom. Now we make the appropriate substitution. Let's transform this integral, which is expressed solely in terms of x, all in terms of u. So we get the integral, sine x on top, we leave it. There's nothing to do. But cos, we're substituting it with the letter u. And dx, we're replacing it with du over negative sine x. Notice that the sine of x is cancelled. And here we have to be careful. Don't forget you have a negative. So let me take that out. Whenever I'm dealing with constants, I like to put them in the front. So treat it as a negative 1 on the outside. And if you're thinking, well, the negative was on the bottom, shouldn't that change the fact? No, because if you have 1 over negative 1, or negative 1 over 1, or negative 1 divided by 1, it doesn't matter where the negative is. This is all the same thing. It all means negative 1. Okay? So we pull out the negative 1, and we're left with simply 1 over u du. How do we integrate this? Well, we could rewrite 1 over u as u to the negative 1. Right? And now you could apply power rule. If you apply power rule, you get negative 1 times u to the negative 1 plus 1 is 0 divided by 0. This is where you know you made a mistake. If you tried applying power rule here, that's wrong, right? We cannot divide by 0. And making this mistake is a good thing, because you know if you did make this mistake, you have to go back and remember, oh, well, I can't divide by 0, so this isn't the right rule. I shouldn't be using power rule. I should be really using the fact that u to the negative 1 is 1 over u, or 1 over x. You can think of it as 1 over x. And we know the integral of 1 over x, or 1 over u, is ln. So this is negative ln of u plus c. Okay. And now we substitute the u back with what we started with. In this case here, negative ln of cos of x plus c. And this is the final answer. We're done. So if you got up to here, good job. But wait, what did we start with? We started with ln of secant. Here we have ln of cos. That's not the same thing. Well, keep in mind we still have the negative in the front. And one of the properties for logarithms is if you have a multiplication of a value in the front, we can put it in the exponent inside the log. So let's go ahead and do that. This is equivalent to ln of cos of x, all that to the negative 1 plus c. So you're taking the negative 1 in the front of the ln and bringing it into the exponent of the cos. Well, what's cos inverse? Or what's the reciprocal of cos? This could be rewritten using our trig properties as secant, because 1 over cos is equal to secant. And this is the answer in the form that we have it. Okay. So I hope this video helped. I hope you have a better understanding of u substitution. So keep practicing, and I'll see you in the next video. Take care.